Hi guys, welcome to video 5.2.3. We're going to look at some other titration issues. We're going to look at two problems in this video. So suppose a 50 ml sample of 0.2 molar ammonia solution is titrated with 0.4 molar hydrochloric acid. So we have a weak base titrated with a strong acid there. We're going to create a buffer at some point. Calculate the milliliters of hydrochloric acid required to reach the pH at the halfway and the equivalence points. Okay, and then we'll sketch the graph once we're all done. It gives us the KB already, so we're good with our KB. Okay, so the first step, let's go ahead and do first our equivalence point. Well, first, before anything, let's write an equation so we see what's happening here. So we have your NH3, that's your ammonia, plus H+, that's from the HCl, going to NH4+. And you can include water if you want, but I'm not, because this is just a net ionic equation. So let's figure out how much acid I need to add to reach my equivalence point. And then, of course, half of that will be to the halfway point. So I have 50 milliliters of ammonia, and my ammonia concentration is 0.2 molar, so 0.2 moles NH3 over 1,000 milliliters, so that's per liter. This is a 1-to-1 stoichiometric ratio here. This is our balanced equation. So 1 mole H plus is all it takes to neutralize 1 mole of ammonia. And then, of course, I have my concentration of my acid. That's 0.4 molar. So I know I need 0.40 moles of H plus for every 1,000 milliliters. And so go ahead and plugging this into your calculator, or even canceling some things first. So these thousands go away, right? They're on the opposite side. So that's a nice easy thing to cancel. You don't have to plug in. You can also cancel the 0.2 and the 0.4. So anyway, plugging all this in, you get 25.0 milliliters of hydrogen ions, or the acid, added to reach the equivalence point. And to get to the halfway point, of course, you're going to need half of that. So that means you have 12.5 milliliters of acid added to reach the halfway point. All right. And we know that, so it's telling us how many mils of HCl is required to reach the halfway point. Okay, check, we've done that. And what's the pH at the halfway point? Well, at the halfway point, we know at halfway point, the pH equals the pKa. And so our pOH is going to equal our pKb. Because we have our Kb, we don't have our Ka here. And so our pOH equals the negative log of 1.8 times 10 to the negative 5. And that was given to us above right here. So pOH equals 4.74. And 14 minus 4.74 will give us our pH. So pH equals 9.26 at the halfway point. Okay, so that's our first pH. All right, next, at our equivalence point, we've needed to use 25 milliliters of acid added. The only thing left to calculate here is the pH at our equivalence point. So at the equivalence point, you've titrated all of your weak base, so that means the only thing you have left is the conjugate acid. So you've titrated all your ammonia, you've added just the right amount of hydrogen ions, and now the only thing you have in solution is your ammonia. So this now becomes an equilibrium problem because, of course, your ammonia is a weak base and it dissociates just a little bit. So we need to figure out what that is. So to do that, just like before, we're going to use our ice table and we're going to use our Kb equation. So at equivalence point, we have only NH4+. So I'm going to go ahead and figure out the initial moles that I have of my NH4+. So initial moles And we're going to calculate that from our initial moles of NH3, because if all the moles of NH3 dissociate, we have exactly the same number of moles of NH4+. So we added 50.0 milliliters at 0.200 molar. When you calculate this, you should get 10 millimole of NH4+. At the equivalence point. So at this point, it's just a weak acid solution. So if from this we figure out the number of moles or millimoles, we can also calculate the concentration of NH4+. So the concentration of NH4+ is equal to 10 millimoles, so we're going to be moles per liter. So 10.0 millimoles over, now I can keep this in milliliters because milli will cancel milli and you'll have moles per liter. And we need the total volume of our solution that we have at our equivalence point here. So we started with 50 milliliters of ammonia, and then we had to add 25 milliliters of our acid to it. So overall we have 75 milliliters. So 75 milliliters. Milli cancel milli. You have moles per liter. So your molarity is 0.133 molar. Now that I have my concentration, I'm going to go ahead and write or do my icebox. And so this is just a weak acid problem. So I start with my weak acid. So I'm going to write my dissociation equation for NH4+ in water. Goes back and forth to make some ammonia again, plus H3O+, or H+. You can write it either way. Initial, change, and ending. So this is going to be molar. So I calculated my initial moles here as 0.133 molar. Haven't formed any product yet. Minus X plus X plus X. 0.133 minus X. We formed X and X there. And of course H2O doesn't count because it is a pure liquid. Pure liquids don't count. Okay, this is an acid dissociation, so we need the Ka. We're only given the Kb. So let's go ahead and figure out our Ka. So we're given the Kb, we always know Kw. So that equals 1.0 times 10 to the negative 14 over 1.8 times 10 to the negative 5. That was the Kb we're given in the problem. Equals 5.6 times 10 to the negative 10. So that's our Ka. So we are going to write our Ka expression just the same as we always do. Ka equals products over reactants. So NH3, H3O plus my reactant here, NH4 plus. Plugging in the numbers, X and X for the top, so X squared. 0.133, ignoring that minus X, divided by 0.133, assuming that X is very, very small. And you get X equals, oh wait, I'm sorry, this whole thing should be set equal to the Ka, I didn't write that. So equals 5.6 times 10 to the negative 10. So here's your problem that you're solving right here, just at the end. Multiply these together, take the square root to get X, and we get X equals 8.6 times 10 to the negative 6 molar. And that equals the concentration of H+. So we can get the pH from the H+ concentration. So our pH equals negative log of H+, which equals negative log of 8.6 times 10 to the negative 6 there, because our H+ is the same as H3O+, and X is equal to that number, 8.6 times 10 to the negative 6. And that equals 5.07 at the equivalence point. Your pH is 5.07 at your equivalence point. Okay, so at this point, we've calculated both of our pHs, we've calculated both of our volumes. Now sketch the titration graph. Okay, sketching our titration graph at the bottom here. So on the bottom, let's see, I'm going to have 0, and then we're going to go pH all the way up to 14. So 2, 4, 6, 8, 10. Oh, 12. Oh, just want to use that. 14. So pH up to 14. And then here we're going to have milliliters added. This doesn't need to be perfect because it says sketch. So this is going to be milliliters of H plus added. And now we're going to go ahead and sketch our 3 points. So I'd like you to please pause the video, sketch the 3 points, starting halfway in equivalence points, and then come back to make sure you got them right. Alright, your starting point is going to be somewhere around 12.5 or so. Your halfway point, and that's when you haven't added any milliliters of hydrogen ions. Your halfway point here is going to be when you have added 12.5 milliliters of your acid, and your pH, let's see, was 9.26, so 9-ish. So let's see, 12.5, 9-ish, right there, maybe. Okay, and then your equivalence point was when you added 25 milliliters. So here you added 25 milliliters to reach the equivalence point, and the pH was 5.07 at that point. So 25 and then 5.07, that's about here. So connecting these points with a curved line, so remember you're kind of going flat through this whole buffer region. This should be flat. And then you start to drop very sharply here at your equivalence point and then level off again until you get low. Okay, so this should be a straighter line, but I sketched it. Alright, so this labeling here, this is your starting point. And here you only have an H3. This is your halfway point. And since you've titrated half the moles of your weak base, the concentration of your NH3 is equal to the concentration of ammonium, your conjugate acid. This is the equivalence point. And here you've titrated exactly all of your ammonia, so the only thing you have left is ammonium, or your conjugate acid. So that would be your titration curve for example number 3. So let's go ahead and take a look at example number 4. Okay, in this last video, in this last example, we are going to take a look at a polyprotic acid. So we're going to take 40 milliliters of 0.1 molar sulfurous acid. This is not sulfuric, this is sulfurous acid. So it's diprotic, meaning it has 2 hydrogens to remove here. And it's titrated with a 0.1 molar sodium hydroxide solution. That's a strong base. Calculate the milliliters of sodium hydroxide required to reach its halfway point and equivalence points. Sketch the graph. Alright, so this is a diprotic acid. Protic acid. That means 2 halfway points and 2 equivalence points. Alright, let's go ahead and write an equation so we see what's going on here. So H2SO3, sulfurous acid, plus hydroxide from that strong base. We don't care about the sodium. This is net ionic. It's going to yield HSO3 minus plus H2O. Okay, so that's our first association there. So here, we're going to figure out how many milliliters it takes of our strong base to titrate to our first equivalence point. So we have 40 milliliters of a 0.1 molar sulfurous acid solution. So 0.10 moles H2SO3 per 1,000 milliliters. This is a 1-to-1 ratio. I have my molarity of my hydroxide, 0.1 molar. And I get 40 milliliters. And this is equivalence point number 1. Okay, equivalence point number 1. So that means my halfway point number 1 is going to be what? It's going to be 20 milliliters. So down here, I'm just going to do some bookkeeping. So halfway point number 1, add 20 milliliters of OH minus. We also know that the concentration of your acid, H2SO3, is going to be equal to the concentration of its conjugate base, which is HSO3 minus, and that we know that pH equals pKa 1. So since this is the first dissociation, your first pH depends on your first pKa. So we have our K1, so we take the negative log of that to get our pKa like we have been, and that's going to be equal to 1.82 for our pH. And I only did that pH because that was an easy pH. So at the equivalence point, it's not so easy because we have to do an ice table and we have to do the Ka, which we don't have to do in this problem, so I'm not going to do that, but we did that in the previous problem. So the equivalence point number 1, we calculated that here. That's 40 milliliters. So add 40 milliliters of hydroxide. And like I said, we are not going to calculate our pH for this one. You could if you wanted to, but you don't need to. Problem doesn't ask you to. Halfway point number 2. To get to halfway point number 2, we need to add 20 more milliliters to pull off the next proton. So we added 20 to go to halfway point 1, 40 to go to the equivalence point 1, and now we're going to add another 20, so we get a total of 60 milliliters of hydroxide. And then when that happens, you have your acid and its conjugate base, so HSO3 minus, equal to the concentration of its conjugate base. And tearing off that last proton there, you get SO3 2 minus. And we know that pH equals pKa at any halfway point. This is the second proton to come off, so there's our K2. So take negative log 1.0 times 10 to the negative 7. That's just 7. So our pH equals 7. It's exactly neutral at halfway point number 2. The last equivalence point, I'm sure you can guess how much we need to add. Add 80 milliliters of OH minus. And again, I'm not going to calculate my pH there. You could do that if you wanted, but you don't have to. So the pH of the equivalence points aren't calculated. So the last part of the problem asks us to sketch this titration graph. So I'd like you to pause the video and go ahead and sketch the titration graph. Here's my graph. It's just a sketch, so it doesn't need to be totally neat and perfect, but I do have my pH on my y-axis, milliliters of hydroxide added on my x-axis, and I have sketched my important points on here. I know the pH at 2 points, so at my halfway point number 1 and halfway point number 2, so I just included those, and I know my pH of my equivalence points is somewhere between it, so I just sketched it knowing those 2 points. Okay, so my starting point, I only had sulfurous acid. Then I get to my my halfway point number 1, where I have sulfurous acid. That's equal to its conjugate base right there. At my first equivalence point, I only have my conjugate base, but now that's going to act as my acid for the next reaction. So now this is going to dissociate. This H plus is going to come off, and we're going to get our acid concentration at equivalence point 2 at a pH of 7 equal to its conjugate base. And then finally, lastly, at my very last equivalence point, I only have the SO3 2 minus left in solution, and your pH just continues to climb as you go. So that is the end of titration talk, and that's the end of video 5.2.3.